Okay, so sorry about the way the last video ended. I believe you could hear me talking, but not actually see what I was pointing to. Alright, so let's give this another try. So we left off talking about the idea of the system, the surroundings, and the universe. Okay, so let's talk about how heat transfers between these. Okay, so we have either an exothermic process or an endothermic process. With an exothermic process, heat is leaving the system into the surroundings. With an endothermic process, heat is leaving the surroundings into the system. Okay, so exothermic heat flows from the system into the surroundings, and an endothermic process, heat travels from the surroundings into the system. Okay, so let's look at these a little bit deeper. Okay, so when energy leaves the system and flows to the surroundings, the energy of the system decreases. Okay, so we designate this with a negative sign. So we have maybe like a negative delta H. Okay, and the reason we do this is because we're talking about this from the point of view of the system. Okay, so an example of an exothermic process would be like striking a match. So if we strike a match and we put our hands close to it, we can feel the heat coming off of it. So this is an exothermic process. Okay, so energy leaves the system and goes into the surroundings. And from the system's point of view, the energy of the system is going down, while the energy of the system is going up. So basically we have energy or heat flowing from the system to the surroundings. We can also have an endothermic process. So here, heat enters the system from the surroundings. Okay, so from the system's point of view, its energy increases. Okay, so we give this a positive sign. So we'd have just maybe a positive delta H instead of negative. Okay, and we call this an endothermic process. So an example of this would be like taking an ice cube and putting it on the counter. Okay, so melting water, or melting ice, excuse me. This would be an endothermic process. So it requires heat to go from the surroundings into the system. Okay, so heat enters the system, or energy enters the system from the surroundings. Okay, and so from the system's point of view, the energy of the system increases, and the energy of the surroundings decreases. Okay, so if we put these all in the same place, so we have Q, which is heat, W, which is work, and then delta E and delta H. Okay, so if I have a positive Q, system is gaining thermal energy. If I have a negative Q, the system is losing energy. Okay, if I have a positive W, okay, work is being done on the system. If I have a negative W, work is being done by the system. And then just like we looked at, if I have a positive delta H, energy flows from the system, flows into the system. In other words, it's an endothermic process. And if I have a negative delta H, or delta E, energy flows out of the system. In other words, it's an exothermic process. Okay, so let's look at some of these. These are just a few different things that can occur. Okay, we want to decide whether they're endothermic or exothermic. So is heat going in or is heat coming out? Okay, the first one. So we're going to evaporate liquid water. So we have to put energy in to evaporate water, or do we have to take it out? Okay, so of course we have to put energy in. So that's endothermic. What about combustion of fuel? Okay, so if we think about this one, do we give off energy when we combust the fuel, or do we put in energy? Okay, so for instance, if we in our cars and we're giving off energy, does it get hot or does it get cold? In other words, does your car engine get hot or cold? Okay, so combustion of fuel. Of course, it gets hot. Okay, so it's an exothermic process. Okay, number 3, condensation of water vapor. Essentially, this is the opposite of number 1. So we're going from gaseous back to liquid. Okay, so does it take energy to put in or take out? Okay, so this is sort of like what happens with dew in the morning. This is an exothermic process. Okay, number 4, cooking an egg. Okay, so if I cook an egg, do I put energy in or do I take energy out? Do we cook with something that's hot or do we cook with something that's cold? And of course, it's an endothermic process because we have to put energy in. Okay, mixing water and an acid. Okay, these last two you may not know right off the bat. Okay, but if I mix water and an acid, it's going to be exothermic. It's going to heat up. Okay, what about dissolving ammonium chloride in water? Okay, well this is an endothermic process. So generally speaking, if you want to dissolve more of something, you put heat in. Not always, but most of the time. So for instance, if you're making sweet tea and you want to put more sugar into it, okay, you heat up the water, or you put the sugar in when it's hot, I should say. Okay, so it's an endothermic process. Not always, but in most cases. Okay, so just some unit conversions. So 1 calorie is 4.184 joules. 1 dietary big C calorie is equal to 1,000 calories, or 1 kilocalorie. We kind of talked about that already. And 1 kilowatt hour is 3.6 times 10 to the 6 joules. So just make sure you have a good handle on those. Okay, so now we're going to get into sort of applying some of these ideas and learning some new definitions and getting into some equations. Okay, so the first thing here, heat capacity. Okay, so this is the amount of energy, in other words Q, required to raise an object's temperature by 1 degree C. So we can set up this equation. Q is equal to C times delta T. Okay, and here C is the heat capacity of a substance. Actually, this should say of an object. When we talk about heat capacity, we talk about objects, and we'll see a term in just a second, which is when we talk about a substance. Okay, and delta T is, of course, just the change in temperature. So if I want to know how much heat it takes to heat up an object, okay, we're going to talk about big C, so heat capacity times delta T. Okay, but then we have specific heat. Okay, so when we talk about specific heat, we're talking about a substance. Okay, so specific heat is the amount of energy required to raise the temperature of 1 gram of matter by 1 degree C. So notice this time in our Q equation, we have to take mass into account. Okay, so Q is equal to M times C times delta T, and we put a little S by the C to let us know it's specific heat, not just heat capacity. Okay, here M is the mass of the substance, delta T is the change in the temperature of the substance, and then Cs is the specific heat for a substance. Okay, so very subtle difference between those two equations. Just here we're talking about Cs, which is specific heat, and we have to account mass. So the reason we don't account for mass when talking about heat capacity is that it's already part of big C. So you would already measure this for something like a calorimeter or something like that. Okay, so here's a question. So what is the heat in joules required to raise the temperature of 25 grams of water from 0 degrees C to 100 degrees C? And then it wants to know what is the heat in calories. Okay, and they give us the CS for water. Okay, so first thing we want to do is just to collect terms. Okay, so we'll just collect our equation, collect the terms that they gave us. Okay, so we were given that the initial temperature is 0 degrees C. We're given that the final temperature is 100 degrees C. We have a CS, a specific heat for water, 4.184 joules grams degrees C. Okay, and then we have a mass of 25 grams. Okay, and we're looking for Q. Okay, so let's just find delta T first. So remember, it's final minus initial. Okay, so this will just be 100 degrees C minus 0 degrees C, which is of course 100. Okay, then just plug back into our equation. Okay, so we know that Q is equal to M times CS times delta T. So now just plug in what we know. Okay, and it gives us Q in joules. Why in joules? Okay, because we have grams with grams, C with C, and we're left with joules. Okay, but now we have to convert, because that's what they asked us to do. They asked us to convert it to calories. Okay, so just copying our equation again, we know the heat in joules now. Okay, now we want to convert it. Okay, so we know that 1 calorie is equal to 4.184 joules. Okay, so we just set up our equation. Okay, so we take our heat in joules, and now we want to convert it. So we'll put 1 calorie is 4.184 joules, so joules on the bottom so that we can cancel with joules. Okay, so just divide by 4.184. Okay, and it gives us 2.5 times 10 to the third calories. I'm not so concerned what the number is right now. Okay, but we're in the right units. Okay, so good. Okay, so one for you to try here. Okay, so it says, suppose you find a copper penny in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow to the temperature of your body? Again, it says assume the penny is pure copper and has a mass of 3 grams, and they tell us the CS for copper. Okay, so give this one a try, and then we'll go over it. Okay, so let's take a look at this one. Okay, so first thing, let's just collect our terms. Okay. So we were given that our mass, M, is equal to 3.10 grams. Okay, and this is of copper. Okay, then we were told our initial temperature. Okay, so remember it's starting from minus 8 degrees C. Okay, then our T final. Okay, 37 degrees C. Okay, and then they gave us CS for copper be equal to 0.385 joules over grams times degrees C. Okay, so what we want to know is how much heat is absorbed by the penny as it warms to body temperature. Okay, so let's move this up. So how will we figure this out? So we obviously want to use our Q equation. So we know that Q is equal to M, since we're dealing with copper, an actual substance, not just an object, okay, times delta T. So first we want to find delta T. Delta T will be equal, remember, it's T final minus T initial. Okay, so this will be equal to T final minus, oh, let's see here, eight degrees C. Sorry, I just wrote T final, huh? That doesn't really make any sense, does it? So 37 degrees C minus negative 8 degrees C. Okay, so delta T will be equal to total of 45 degrees C. Essentially what you have is 37 plus 8. Okay, now we can just plug into our equation. So we'll say Q equal to, so our mass was 3.1 grams. Sorry, not equivalent, but equal. Times CS, they gave us 0.385. Why my 5 looks like that? Joules, grams times degrees C. Times, and then our delta T is just 45 degrees C. Okay, so we have grams canceling with grams, degrees C canceling with degrees C. So we're just left with joules. Okay, so our Q becomes 53.7 joules. Okay, so hopefully you got that one. Okay, so back over to the slides. Okay, so here's another way to find specific heat of a substance. Okay, so here we have an iron cube with a mass of 55 grams. Okay, so we could potentially take this to our balance and just weigh this iron cube. Okay, then we're going to heat it to 99.8 degrees C. So maybe we put it into some hot water or something like that. Okay, so the heated cube was then dropped in 225 grams of water at room temperature at a temperature of 21 degrees C, sorry. So after 10 minutes, the water in the metal core, and the metal came to a temperature of 21.3 degrees C. Wants to know what is the specific heat capacity of the metal. Okay, so how can we solve this? Okay, so what we need to know about this, firstly, is that the Q of the metal is equal to the opposite of Q of the water. Okay, so let's take a look at this one. So I'm going to sort of just carry us over to our paper again. Okay, let's take a look at this one. Okay, so what did they tell us? What information did they give us? So first thing they told us was we have 55 grams of iron. Okay, so we have 55 grams of iron, and it was heated to 99.8 degrees C. Okay, so we know that the cube was dropped into 225 grams of water at 21 degrees C. So 225 grams of water. Okay, what was it? It was 21 degrees C. Okay, and then it tells us after 10 minutes the water in the metal came to a temperature of 23.1 degrees C. So T final equals, was it 21 or 23? Don't want to mess you up. 23. Okay, and it wants to know what specific heat capacity of the metal. Okay, so we want to say this. We want to say Q of iron is equal to minus Q of H2O. Or in other words, we could say Q of iron plus, oop, that's not right. It's going to make an uppercase Q. Q of H2O is equal to 0. Just rearranging that equation. Okay, and what we want to know is, what is, that's not right, that's not what I want. I know what is CS, I'm going to write it up here just for space. We want to know what is CS for iron. Okay. So how can we solve this? First thing is, so if we just try to solve for Q of iron, okay, so we don't know how much iron changed, how much heat it took. Okay, so we can just say we have 55 grams of iron times its specific heat capacity times what? Well, we need to know the delta T. So the delta T is going to be equal to, so final minus initial. It was initially at 99.8 degrees C. Okay, so delta T for the iron so delta T for the iron is essentially minus 76.7 degrees C. Okay, so this equation times minus 76.7 degrees C. So what we essentially end up with is Q of iron equal to, and let's just collect the grams and the temperature. This comes to 4218.5 times CS. So we'll need this later. Let's just draw an arrow to it. Okay. So what we can solve here is the Q for water. Okay, so we'll say QH2O is equal to, they told us 225 grams times 4.184 CS for water, and that's joules double check my unit. Man, I don't want to get those wrong. Oh, they don't tell us here, do they? Okay, so joules over grams times degrees C. Okay. So that's going to be times what? So the D is the delta T for the water. Okay, so they tell us the initial temperature of the water is what? 21 degrees C. The final temperature is 23. Okay, so 23.1 degrees C minus 21 degrees C, which gives us 2.1 degrees C. Okay, so we'll just say times 2.1 degrees C. Okay, so Q for water comes out to 1977 joules. So grams, degrees C with degrees C, we're left with joules. Okay, so this is Q for H2O. Okay, so what can we do with that? So if we go back to our equation, we said that Q of iron plus Q, or sorry, let's do it this way. Well, no. Yeah, so plus Q of H2O is equal to, and we said the Q of iron, so if we go back to our equation up top, Q of iron is equal to 4218.5 times CS, and that's going to be plus the Q of water, which we just solved for, 1977 joules. Okay, so basically we need to solve this for CS. So we'll say minus 4219 times CS is equal to minus 1977 joules. Okay, divide both sides by minus 4219. Okay, so CS essentially is equal to 0.469 joules degrees C times grams. Okay, so I know that's a little bit of a convoluted way to get there, and I probably wouldn't ask you one quite this complicated. Okay, but I just wanted to show you how you can use these ideas. Okay, but that's probably a little more than I would give you. Okay, but that's how we could use it. Okay, so let's go back to the slides now and continue on. Okay, so we're going to start talking about calorimetry. Okay, this is essentially a way of measuring how much energy is contained in a system. Okay, so this is sort of the technique they use when they talk about calories in food. Essentially what they do is burn it, okay, and they measure that energy change, that temperature change. Okay, so formally a quantitative method determine the heat flow between two systems and their surroundings. Okay, so systems can be about physical changes or chemical changes. Okay, so physical, in other words, a phase change, so from water to gaseous vapor or gaseous water, or it can be chemical, so actual chemical reaction. Okay, so it measures the change in energy under constant pressure conditions. Okay, so we're going to measure the heat flow between the system and the surroundings and the workflow between the system and the surroundings. Okay, so for example, this is one very often used in general chemistry lab, which is just a coffee cup calorimeter. Okay, so we have a thermometer used to measure the change in temperature, a glass stirrer just used to stir the mixture, a cork lid just to hold the heat in so we don't lose too much, and then two nested foam cups, okay, just to sort of insulate it. Okay, with a simple device like this, you can, for instance, mix an acid and a base measure the change in temperature and see how much energy was exchanged between those two systems. Okay, the way we do this, remember that Q is equal to mass times specific heat times delta T, where Q is the heat lost or gained, and is related to M, the sample mass. Okay, so we need to know some things like, for instance, usually when you use calorimeters, you want to know like the mass of water that you put in, those kind of things. Okay, delta T will be the change in temperature. Okay, and then CS is specific heat. So just like what we just talked about. Okay. So suppose we have a 20-gram sample of aluminum. It's cooled from 310 degrees C to 37 degrees C. What amount of energy in joules is lost by the aluminum? And they give us a specific heat. Okay, so we'll get back to calorimetry, but let's just try another specific heat problem. Okay, so give this one a try, and we will go over it together. Okay, so remember that heat gained or lost, Q, is equal to the specific heat times the mass times delta T. Delta T is equal to T final minus T initial. Okay, so let's try to solve this one. Okay, so it asks us if 25 grams of aluminum is cooled, and they give us some temperatures, what's the amount of energy lost by the aluminum? Okay, so remember Q is equal to M times CS times delta T. Okay, so they gave us an M equal to 35 grams. They told us T initial was equal to, so it was cooled from 310 to 37, so our initial is 310 degrees C. T final equal to 37 degrees C. Sorry, that's not a 3, that's supposed to be a 7. And then our CS equal to 0.897. And that's joules per grams over grams degrees C. Excuse me, losing my voice a little bit. Okay, so delta T will be equal to 37 degrees C minus 310 degrees C. So that gives us a minus 273 degrees C. So our Q will be equal to 25 grams times 0.897 joules grams degrees C times our delta T, which we just said was 273 minus 273 degrees C. Okay, so if we just multiply those numbers together, we end up with 6,120 joules. But notice it's asking how much is lost. So remember, we have a negative sign. Okay, so this is going to be a negative 6,120 joules. Okay, so no big deal. That's basically the same thing as we were doing. But what I wanted you to recognize was that we're actually losing energy in this. Okay, so how much energy is lost? Okay, so basically that's an example of the equations that are used when you're doing calorimetry. Okay, so here we have a basic bomb calorimeter. Okay, so this is called a bomb calorimeter because it's essentially a sealed container. So this is the bomb part, sealed container. So you put a sample into the sealed container. Okay, then you have oxygen, and you seal it tightly. Okay, and then you put all that down into some water inside of the calorimeter, and it has an ignition wire attached. Okay, so you can ignite the oxygen. Okay, and you can measure the amount of heat transferred to the water, and then from that you'll understand that it's basically the heat evolved from combusting the oxygen plus the sample. Okay, so you do these where you know how much energy the oxygen will give off. Okay, then you count the difference to the actual sample. Okay, so some of the heat of the reaction warms the water. So therefore, Q water is equal to specific heat times the water mass times delta T, of course. But some of the heat actually also warms the calorimeter. So therefore, Q of the bomb, so the actual bomb piece, the calorimeter, is equal to the heat capacity. So remember, heat capacity refers to an object times delta T. So the total heat evolved is equal to Q total is equal to Q water plus Q of the bomb. Okay, so this is the equation we need if we're talking about this kind of calorimeter. So it just accounts for the actual calorimeter itself. It also accounts for the water. Okay, so what would we do with this? So suppose 1 gram of octane is burned in a calorimeter containing 1,200 grams of water. Temperature ranges from 25 degrees C to 33 degrees C, and CS for water, of course, is 4.184 joules grams degrees C. Okay, they tell us the heat capacity of the calorimeter. Okay, and this would be done through several trial experiments. Okay, so it says calculate the energy of the combustion reaction, and then calculate the energy for 2 moles of octane. And they give us an unbalanced equation. Okay, so first thing we want to do, balance the equation. Okay, so hopefully you can balance combustion equations by now. So that was covered in the gases chapter, so we should be familiar with that. Okay, then we want to calculate the energy transferred from the reaction to the water. Okay, we're going to do that just with our Q equation. So Q is equal to CS of water times the mass of water times the delta T. Okay, so just like we did before. So how much energy is transferred from the reaction to the water? Well, minus 41,200 joules. Okay, and then calculate how much energy is transferred from the reaction to the bomb. Similar equation, but this time we use the heat capacity for the bomb times delta T. Okay, so Q is equal to 837 joules degrees C. Notice there's no grams involved in this because we're not taking apart the mass in any way. Times delta T, so 6,860 joules. Okay, so the total energy evolved for 48,060 joules. Okay, so the answer to the question is minus 48.1 kilojoules for 1 gram. Okay, so this is just for 1 gram. But for 2 moles, we have to convert basically octane from grams to moles. Find out how many moles we have. Okay, we can set this ratio up. Okay, so we have this many moles over how many joules were evolved. Okay, is equal to 2 moles over X. Okay, and the reason we can do this, remember, is because this is for 1 gram, basically. That's the information we have. But if we want to know, since this is in moles now, we can say for 2 moles over X, then solve for X, and then I'll tell you how many moles, or how much per 2 moles. Okay, I probably wouldn't give you something like this last part, but it's good to know that you can also put this in terms of how many moles instead of just per how much mass. Okay, so probably the last question for this video, and I will probably just put this up along with the first half, and then we'll cover the rest of the chapter in another video. Okay, so it says, after stopping at her grandson's favorite hamburger drive-thru place, Grandma places her hot cup of coffee on the dashboard, but her change into a purse. Just as Grandma is closing her purse, her grandson speeds off from the drive-thru window, resulting in the hot cup of coffee spilling all over Grandma. Because of the severe burns resulting from the spilled coffee, Grandma and her grandson have decided to sue the hamburger establishment for damages incurred from the incidents. Okay, so sort of a funny scenario, but what's the question here? So how much energy did Grandma's hand absorb when the hot coffee spilled on her hand? Okay, so they tell us a hot cup of coffee contains 100 grams of water, okay, at 100 degrees C. Grandma's initial skin temperature was 37 degrees C. They give us the delta H for vaporization, and the specific heat capacity for water is 1 cal per gram per degree C. Okay. So the first thing we want to do is calculate transfer of energy the transfer of energy from the hot water to grandma's hand. Okay, so Q is equal to the mass of the water times the specific heat times delta T. Okay, so just like we did before. Okay, so 6.3 times 10 to the second calories of energy were transferred from the water to her hand. Okay, but there's also a second part. Okay, so due to the steam turning to liquid, that's also associated. Remember we said going from a gas to a liquid? Okay, was endothermic? I'm sorry, exothermic, yeah. Exothermic. Okay. In other words, that's going to give off some energy too. Okay, so we have to do that calculation. And they kind of told us this number, 540 calories per gram. We know how many grams. Okay. So we can see how many calories of energy are just from the steam going back to a liquid. So that means the total energy absorbed by her hand was 6.03 times 10 to the 4th calories. So lots and lots of calories. But the point here is it wasn't only from the hot water, but it was also from the steam. And again, this is a problem I probably wouldn't ask you to do. This is kind of beyond what I would expect from you right now. But I think it's kind of interesting that not only does the hot water transfer energy, but also the change from